That was a great talk that Liz Parrish just gave. I was hoping she would spend more time talking about telomeres because I'm not going to talk about telomeres today, but I want to start off with saying that ever since I've been a little kid, I have been very interested in curing aging, and it's been an obsession my entire life. I'm frustrated by the fact, and everybody knows that my background is, or my focus is on telomere biology. And the frustrating part of that is that I constantly wonder why I don't have more competition. Okay. And so I think and I welcome competition. I would help competition because bottom line, I want to see my own aging cured, even if I'm not the one that does it. So I want to help anybody who's actually going to help me cure my aging. But I'm wondering if maybe I haven't been really presenting it correctly or at least explaining how important telomere biology is. And so that's what I'm going to try to do today. I'm not going to be talking about telomeres very much, but I want to start off with the fact that we do have this theoretical maximum of 125 years. It's been published in several different papers. For a long time, people really didn't know why, but it's 125 years regardless of your genetics and lifestyle. And I can say that poor genetics and poor lifestyle can accelerate the aging process, and that's why none of us actually ever lived to be 125. But even if we did have the perfect genetics and perfect lifestyle, we still would be limited to 125 years. And so I'm trying to do a series of talks on curing aging. And I figure in order to cure aging, we really need to know what aging is, why we age, how we age, and then how to undo aging. And I can't talk about all these things in one session today. And so I've been trying to make several talks on these things. And today what I'd like to do is I'd like to focus on how do we age. And as I said, I'm not going to be talking about telomeres very much because that's more on how do we undo aging. And so if anybody wants to learn more about my background or see other videos of me speaking about telomeres, they can go to www.sierrasci.com. Because of lack of time, I'm also not going to spend a lot of time talking about my biography and my track record, but you can also find that information at sierrasci.com also. So I believe that aging is really just multiple tissue and organ failure. And what I want to do is I want to mechanistically explain what is happening in all this process, because we are practically completely just tissue and organs, and it's all about those things all failing. Okay, so this is a typical organ. Now, not all organs are going to look like this, but I want to make this like symbolic of organs in general, including blood, which is an organ, or a tissue at least. And it has its bone marrow and its serum and everything in it. So, but what I want to do is just kind of use a generalized concept here. And first, let's have this organ or tissue. And along the edge, or sometimes inside, depending on the organ or tissue, are frontline cells, just like frontline in a battle, okay? These are the cells that see all the action. And the problem is, and step one of aging is wear and tear. Okay. Now, this is what happens to a lot of. Number one, the most important part of aging to begin with is the wear and tear that's occurring in our body. Now, frontline cells typically survive only about 1 year because of wear and tear. And as they get killed or whatever, they become non-functional, they get lost. And that's what happens over and over again. But that's actually okay when we're young, okay? It's not a problem. And that's because there are reserve cells and stem cells. And reserve cells, another name for reserves, I'm trying to use a military kind of battle organization. You always have your reserves to replace the front line. But the reserve cells are also called progenitor cells. And so when we lose a cell, let's say a frontline cell, it's no problem because our other cells can replace through division or moving around, can replace these lost cells. And so that's why it's not a problem when we're young. But the problem is that human cells can only divide a limited number of times. Our cells, both the reserve cells and the stem cells, when we're born, have typically only about 50 cell divisions that they can do. And that's the problem. Okay, so let's even go back before we're born. Okay, from a fertilized egg, your single cell, that cell has the ability to divide 100 times. Okay, it divides once, then it has 99, then your cells, the two cells have 99 divisions they can do. In the 98, 8-cell stage has 97, 16 cells has 96. Okay, eventually we get to a newborn baby. Newborn baby has about 50 cell divisions left in it. Then when you get older and older, they decrease. And when you get pretty old, you've got like less than 10 cell divisions. Now, this isn't all the cells of your body. Okay, this is pretty much just the frontline cells. But some cells in our body don't go through a lot of division. So some cells in our body do have a lot of aging left to do, or a lot of cell divisions left to do. So this is called the Hayflick limit. It was discovered in 1961. And this is actually the problem. Okay, this is the problem because it limits our lifespan and our health span. Even though we're losing all these cells and they can be replaced by reserve cells and stem cells, they can't do it forever because those cells only can divide 50 times. So, and even if you had the perfect genetics, as I mentioned before, if perfect genetics and perfect lifestyle, you still have a theoretical maximum of only 125 years. And that's in a large part probably due to these 50 cell divisions that can occur once you're born. Okay, so as the cells do start dividing, and they start approaching that 50 cell divisions, they become senescent. Okay, and so you can find the stem cells become senescent, the reserve cells can become senescent, the frontline cells become senescent. The frontline cells are the first ones to become senescent, but it's as I'll say later, senescence is something that's involved in a lot of aging. Now, with even more cell division, as you get older, even more cells become senescent. And then, but these senescent cells are still alive. They just function a little bit different. And so they still can suffer from wear and tear. And so eventually one of these senescent cells will become non-functional because of wear and tear. It gets lost. And the problem is nobody is available to replace that cell. Okay, the stem cells are senescent, the frontline cells or the reserve cells are senescent, and so that cell can't be replaced. And when that happens, a lot of times you end up having tissue organ failure. Okay, I'm going to go through a list right now of consequences. One is liver cirrhosis. I'm not going to spend a lot of time on all these diseases, but let me just say, when you drink alcohol, alcohol kills liver cells. That is okay when you're young, because the reserve cells can replace those killed those frontline cells in your liver. But as you get older and your cells start apart, because of the alcohol, the cell turnover is a lot faster than once per year, and as a result, your cells approach senescence at a younger age. So now, when they get senescent, you can't replace those lost liver cells that are caused by alcohol anymore, and you suffer from liver cirrhosis. Okay, so if we could prevent this happen, you probably could drink all your life without liver cirrhosis. But the things are chronic kidney disease, a really classic example of frontline cells being killed at a faster rate, and your other cells become senescent and unable to replace those cells. Dementia, multiple sclerosis, AIDS, all these things. I could go and explain each one in detail, but not with the limited time I have today. Now, there's a lot of things that can accelerate the wear and tear and thus cell division. And I already know high blood pressure, diabetes, alcohol, as I already mentioned. There's risk alleles. Okay, so for instance, if you have a gene that's bad that decreases the lifespan of muscle cells, and so let's say the frontline cells in muscles are a little bit different than this organ shown here, but those cells, they die when you're young, but it's okay at first because your reserve cells can replace those killed muscle cells. But then when the reserve cells and stem cells get senescent, they can't do it anymore, and you get muscular dystrophy. Same is true for multiple sclerosis, Alzheimer's. Inflammation is another accelerator, oxidative stress, pathogens, injuries, air quality. Now, this is likewise for the hallmarks of aging. All the hallmarks of aging are causing accelerated death to cells, which is okay at the beginning. But let me go through all these hallmarks of aging. I'd spend more time on each of them if I had more time. But what I want to do is I want to back up a bit here, okay? And I want to say, do we really need to go and solve all these different problems of wear and tear? Okay, that sounds like a lot of work. Wear and tear is a problem, but maybe we should be focusing more on the limited cell division, because maybe that one thing alone could make wear and tear, in a large part, almost irrelevant, because we can continue to replace these wear and tear symptoms. Not in all cases, but in a lot of cases. And it could have a significant improvement of our overall lifespan. So the question becomes, why is human cell division limited to begin with? Why do we even have a limit? What's causing it, et cetera? And so I used to always think, how could a human cell, know how many times it's divided and how many times it still can divide? And I used to think, from a biological perspective and from an evolutionary perspective, what kind of mechanism could possibly exist in a cell that the cells can count? And the only thing I was ever able to come up with, there had to be something similar to ride tickets, like at an amusement park. You go to an amusement park, your mother gives you a bunch of tickets, gives you 20 tickets, let's say. You go on a ride, you have 19 tickets left because the guy at the ride or the woman at the ride took one of the ride tickets. But you have 19 rides left. So you go on another ride, you have 18 rides left. Now, it was easy to imagine a mechanism like that. And so ever since like college and graduate school, I spent my time thinking about, where are these ride tickets? What could they be? And so that was a big question I had for a long, long time. And but I ended up learning about telomere biology. And while I was leading the team at Geron Corporation to look at this kind of problem, we ended up discovering that the limited number of cell divisions and senescence in human cells, at least, is due to telomere shortening. And we showed this by showing that when we lengthened telomeres, they did not have a limit and they did not go into senescence. So the ride tickets that I mentioned are found at the very tips of our chromosomes, called telomeres. I'm not going to talk much about it. I was hoping Liz Parrish would talk more about it. But I don't want to say that this is the only cause of aging. Okay, there's a lot of things that are causing it, and I don't want anybody to think that I'm saying this, but I will say this. This is a really important slide. No matter what else we do to cure aging, our lifespans and health spans will still be limited because of telomere shortening. And unless we solve the telomere shortening problem, we will never cure aging. And that's what's a key important. And that's why at Sierra Sciences, we are right now 95% focused on telomere biology, even though our focus is to cure aging. And by the way, I use that term, reverse aging. I use that term, cure aging, because that's what my father said when I was like 10 years old. Okay, but now apparently the term curing aging has become more acceptable. But that's what we're doing at Sierra Sciences. That's all we're doing. And I would really love to be able to see that if lengthening telomeres would actually reverse aging. And this has already been shown that it works in human cells in a petri dish, human skin on the back of mice, and also engineered mice. And it's also, as Liz Parrish showed, it's possibly working in Liz Parrish too. And I would just like to see a lot more studies doing it, and also to find ways to make it a lot more affordable than what is presently available, such as the gene therapy. I'm going to end now with, I want to say that, why am I doing all this? And that's, I love living. Okay, bottom line, I love living. And I think living is the greatest thing that ever happened to any of us. And I don't want to see aging, or I don't want to see living become any less lovable for any of us just because of this dumb thing called aging, which, if you ever listen to any of my videos on why we age, you'll see it's all an evolutionary thing that really was unnecessary for the individual. We do not need to age. And I'm working on trying to cure that. And if anybody wants to know more about what we're doing, go to www.sierrasci.com. And I want to thank you very much.
Bill, thank you so much. Fantastic presentation. Any questions? Questions, 1 second. Just get here to the stage.
Oh my God, I was under time. Good.
Sorry?
I was under time. I thought
You were
I-
there. That was fantastic. Very good. Perfect. Any questions? Questions? Nothing? You good? Perfect. So then I have, oh, you have questions, Gary? Okay.
Hey, Gary,
It's
how are you doing? Hey,
Good to see you.
Maria, how are you?
Hey, I was wondering do you know if any of the other treatments being developed, like Yamanaka factors and whatnot, are inducing lengthening of telomeres, and to what extent the telomere lengthening might result in the rejuvenation effects or
That's
cellular
the-
reprogramming? Yeah.
That's the main reason that the Yamanaka factors in any reprogramming works. The main reason why they have the rejuvenation effect is because when you use all the Yamanaka factors, you turn on the telomerase gene and the telomeres get lengthened. Everything else in genetic reprogramming, I think, is actually just de-differentiation. Now, we have done a lot of studies, and we published it in a poster session probably 15 years ago. We've done a lot of studies showing that we have tried all combinations of the Yamanaka factors and other factors that have been essentially discovered. And the only way we can get the telomerase gene turned on is to use all of them. And so, I mean, we were hoping to figure out something that would help us figure out how to turn telomerase on using the Yamanaka factors, but we were unable to because it took all of them to do it before we could actually get the gene turned on. And let me just say, I expected a cancer question, so I was prepared for an answer. So let me just say that there are a lot of people worry about telomerase and long telomeres causing cancer, but there's a lot more papers published showing that the lack of telomerase and short telomeres actually are far more likely to be causing cancer than telomerase and long telomeres. In fact, there's no papers actually showing that telomerase and long telomeres cause cancer. They just suggest it. But there's an overwhelming larger number of publications showing that it's the lack of telomerase and short telomeres that we all have to worry about. And that's why we're all getting cancer at high rates already to begin with. All right, thank you.
Thank you, Bill. Thank you. One more question?
Yeah, Bill, I asked Liz Parris this question. I didn't actually get an actual date or a time window. So when do telomeres actually kick in as far as humans are concerned, as far as the aging process? Where do they really start to make us grow old? At what age? I mean, don't give me an actual number like 20, but can you give us like a time frame? Like, let's say between 20 and 25. Can you give me roughly kind of an age range where it starts to really kick in and really starts to take us down?
I cannot answer that question better than Liz Parrish did. And I thought she gave a really fantastic answer. But the bottom line is that telomeres start shortening from the day we're conceived. Okay, and as I said, they get shorter and shorter, and that's why the Hayflick limit is we have 100 cells and 100 divisions at 99 and 98. But there's no kicking in. It's a gradual process. And the reason why is a gradual process. And if you go to my site, you can see presentations where I've given on exactly the regulation of gene expression, the epigenetics. How does telomere length affect epigenetics? But it is pretty well understood, though we need a lot more work to prove it, pretty well understood that telomeres actually act like enhancer sequences. And the telomeres can fold over and come in contact with genes on the chromosomes. And when they do come in contact, just like enhancers come in contact with genes, they turn on genes or they turn off genes. Now, when the telomere gets shorter and shorter and shorter, it can't reach as far, or it's less effective at even regulating genes that are close. So it's a gradual process. So aging is, we can do studies and looking at epigenetics, and we can see that aging is going on all the time. There is no beginning and end. It's a gradual process all the time. And it just becomes a real problem when a large number of cells start reaching senescence, and that occurs at for different people at different ages, different tissues at different ages, different organs at different ages. And so it's pretty much, there is no answer to that question. It's all a gradual process.
Fantastic. Thank you so much, Bill. Brilliant. Thank you so much for answering the questions and for the fantastic talk. I'm looking forward to see you hopefully in person soon, my friend.
All right. Thank you.
Thank you. Have a great day. Bye-bye. Bye-bye.